The filtrate enters the proximal convoluted tubule, where amino acids, glucose, water-soluble vitamins, and the majority of salts are reabsorbed along with water. Almost 70% of filtered sodium will be reabsorbed here, but the filtrate remains isotonic to the interstitium, as other solutes in a large volume of water are also reabsorbed. Solutes that enter the interstitium are picked up by the vasa recta to be returned to the bloodstream for reuse within the body. The primary convoluted tubule is also the site of secretion for a number of waste products, including hydrogen and potassium ions, ammonia, and urea. Filtrate from the proximal convoluted tubule then enters the descending limb of the loop of Henle. The descending limb is permeable only to water, and the medulla has an ever-increasing osmolarity as the descending limb traverses deeper into it. As the descending limb traverses deeper into the medulla, the increasing interstitial concentration favors the outflow of water from the descending limb, which is reabsorbed into the vasa recta. As the descending limb transitions to become the ascending limb of the loop of Henle, a change in permeability occurs. The ascending limb is only permeable to salts and is impermeable to water. Here the opposite occurs. At the deeper parts of the medulla, salt concentrations are high, but decrease as the ascending limb rises. Thus, increasing amounts of salt are removed from the filtrate as it travels up the loop of Henle. At the transition from the inner to outer medulla, the loop of Henle becomes thicker in what is termed the diluting segment. This isn't because the lumen within the tube has enlarged, but because the cells lining the tube are larger. These cells contain large amounts of mitochondria, which allow the reabsorption of sodium and chloride by active transport. Because so much salt is reabsorbed, while water is stuck in the nephron, the filtrate actually becomes hypotonic compared to the interstitium. The filtrate enters the distal convoluted tubule. The distal convoluted tubule responds to aldosterone, which promotes sodium reabsorption. Because sodium ions are osmotically active particles, water will follow the sodium, concentrating the urine and decreasing its volume. The distal convoluted tubule is also the site of waste product secretion, like the proximal convoluted tubule. The final concentration of the urine will depend largely on the permeability of the collecting duct, which is responsive to both aldosterone and antidiuretic hormone. As permeability of the collecting duct increases, so too does water reabsorption, resulting in further concentration of the urine. The reabsorbed water enters the interstitium and makes its way to the vasa recta, where it re-enters the bloodstream to once again become part of the plasma. The collecting duct almost always reabsorbs water, but the amount is variable. When the body is very well hydrated, the collecting duct will be fairly impermeable to salt and water. When in conservation mode, ADH and aldosterone will each act to increase reabsorption of water in the collecting duct, allowing for greater water retention and more concentrated urine output. Ultimately, anything that doesn't leave the tubule by the end of the collecting duct will be excreted. The collecting duct is a point of no return. After that, there are no further opportunities for reabsorption. As the filtrate leaves the tubule, it collects in the renal pelvis. The fluid, which carries mostly urea, uric acid, and excess ions, such as sodium, potassium, magnesium, and calcium, flows through the ureter to the bladder, where it is stored until voiding.